Hi, thanks for joining us for today's webinar on analysis and design of diaphragms. I'm Alan Adams, Chief Structural Engineer for the RAM Group at Bentley Systems and the Senior Product Manager for the RAM Structural System. In this webinar today, we're going to talk about diaphragms, some code requirements, diaphragm classification, but of greater interest, I think, will be the case study information that I'll present and the conclusion and recommendations at the end. But let's start out. There's a wide variety of diaphragm types and materials. You have floors with concrete fill on metal deck. You've got metal roof decks with non-structural fill, concrete slabs. You've got sloping diaphragms, diaphragms with openings, cutouts, corners. I want to start with a brief overview of the types of diaphragms and go over some terminology so that it's very clear what we're talking about and what we're comparing. ASCE 716 requires that the structural analysis shall consider the relative stiffness of the diaphragms. And then it goes on to describe categorizes three different types of diaphragms. Unless a diaphragm can be idealized as either flexible or rigid, the structural analysis shall explicitly include consideration of the stiffness of the diaphragm, in other words, semi-rigid modeling assumption. So this section of ASCE 7 lists these three types of diaphragms that need to be considered in analysis. And it's instructive to classify diaphragms based on how they behave. So this will facilitate further discussion, especially in regard to the building code requirements for analysis and design of diaphragms and of structures with those diaphragms. First, let me start out by describing the behavior of the semi-rigid diaphragm. Using RAM frame, a module in the RAM structural system, let's take a look at the analytical results of this model. The semi-rigid diaphragm translates and deforms. See, you can see how the diaphragm is translating, but also it's deforming. The rigid diaphragm is infinitely rigid in the plane of the diaphragm. It can translate and rotate, but it cannot deform. So notice here that it's again translating and slightly rotating, but it isn't deforming, it's keeping its shape. The whole keeps its shape, the perimeter keeps its shape. It's not deforming. The flexible diaphragm means analytically that there is no diaphragm. In reality, it's so flexible compared to the frames that it has no influence on those frames. Each frame deflects completely independently. The diaphragm doesn't tie them together in any way. So now for some specifics. An example of a flexible diaphragm might be a metal roof deck without structural fill. Although that won't always be considered flexible, it often will be. With a flexible diaphragm, there's no interaction between the frames. They are free to displace independently of each other. And the frames are much stiffer than the diaphragms. Computationally, this is perhaps the most simple analysis because no elements or restraints representing the diaphragm are included in the analysis. So when you think of flexible diaphragm, think of it as no diaphragm. A rigid diaphragm is infinitely rigid in the plane of the floor. When the diaphragm displaces, all points within the diaphragm move in unison. A concrete slab or a composite metal deck with concrete fill are generally considered to be a rigid diaphragm. In a rigid diaphragm, the frames are all rigidly connected. They work and move as a group. In the analysis of a structure, the rigid diaphragm assumption is often used when permissible because it's computationally efficient. There is a significant reduction in the number of degrees of freedom, resulting in significantly shorter analysis times. Modeling is simplified, especially in the application of story forces. Reporting of results is also more simple and concise. So with a rigid diaphragm, the diaphragm is free to translate and rotate, but there is no deformation. The semi-rigid diaphragm has some diaphragm stiffness, some non-trivial stiffness. There is some interaction between frames based on the stiffness of the diaphragm and on what it can convey to and distribute between the frames. Analytically, this is the most complex diaphragm. Its properties must be modeled, and the diaphragm elements are included with the frame beams, columns, braces, and walls in the structural analysis. The behavior of this type of diaphragm is something between that of the rigid diaphragm and the flexible diaphragm. So a semi-rigid diaphragm not only displaces and rotates, but also deforms. So these are the three types of diaphragms analytically: flexible, rigid, and semi-rigid. I want to take just a brief moment here and talk about some of the code requirements related to diaphragms. And specifically, I'm going to talk about ASCE 716, IBC 2015, and the Eurocode. And it's instructive to compare these various codes and see how different codes approach these similar requirements. And this is not going to be comprehensive. This is just some brief highlights just to point out what we find in the codes. So let's first talk about ASCE 716. That includes a very detailed set of diaphragm requirements. Now, it's important to keep in mind that the requirements there for wind analysis and for seismic analysis are not the same. Chapter 12 is seismic requirements, and Chapter 26 is wind requirements. So as we discussed at the beginning, ASCE 7 defines three types of diaphragms: flexible, rigid, and semi-rigid. This requirement is significant. It has a major impact on the type of analysis allowed and on the time and work involved in that analysis. As the semi-rigid diaphragm is more computationally intensive, it's generally desirable to classify a diaphragm as either flexible or rigid if allowed by the code. So let's investigate now the requirements of the subsections referenced here in this section of the code. Section 12.3.1.1 of ASCE 7 defines conditions whereby a diaphragm may be classified as flexible without any further investigation or computation. Steel decking and wood flooring are explicitly mentioned in this definition. Note that steel roof decking on brace frames automatically qualifies as flexible, while steel roof decking on moment frames does not automatically qualify as flexible, although as we'll see later that it may be shown to be so by further computation. Also note that the code says are permitted to be idealized as flexible. Any diaphragm is permitted to be analyzed as a semi-rigid diaphragm. If you want to go to the effort to model and analyze as a semi-rigid diaphragm, you're free to do that regardless of what other sections of the code here indicate for flexible versus rigid. Section 12.3.1.2 defines conditions whereby a diaphragm may be classified as rigid without further investigation or computation. Concrete slabs and metal deck with concrete fill are explicitly defined as rigid when the diaphragm conforms to the span to depth limit of 3 and has no horizontal irregularities. If the diaphragm does not conform to these requirements, it cannot be analyzed as rigid. Let's now discuss in detail what these two requirements, span to depth ratio and horizontal irregularities, mean. As illustrated here, span is measured between adjacent frames. In this case, there are three spans to be investigated: between grids A and C, between grids C and E, and between grids E and G. And depth is the depth between grid 1 and grid 6. As you can see from this, only long, narrow diaphragms without intermediate frames would fail this requirement. The second condition necessary to consider a concrete slab or composite deck as rigid is that it has no horizontal irregularities. Horizontal irregularity is defined in Table 12.3-1, which lists torsional irregularity, reentrant corner, diaphragm discontinuity, out-of-plane offset, and non-parallel system. So if any of these conditions occur in the diaphragm, it is classified as having a horizontal irregularity, which gets us back to this clause, which says that if the diaphragm is classified as having a horizontal irregularity, it cannot be analyzed as rigid. Finally, if a diaphragm has not qualified as flexible based on the criteria in section 12.3.1.1, nor qualified as rigid based on the criteria in section 12.3.1.2, the diaphragm may still be shown through analysis to qualify as flexible as given in section 12.3.1.3. If the amount that the diaphragm deflects is more than 2 times the amount that the adjacent lateral frames deflect, the diaphragm is considered sufficiently soft that it can be idealized as flexible. Of course, this requires the calculation of the diaphragm displacements. So all of this gets us back to section 12.3.1 that says that if the diaphragm does not qualify either as flexible or as rigid, it must be analyzed as semi-rigid, considering the true stiffness of the diaphragm. Now let's take a look at IBC 2015 and compare it with what ASCE 7 had to say. In section 1604.4 of IBC 2015, it defines a rigid diaphragm in this way. A diaphragm is rigid for the purpose of distribution of story shear and torsional moment when the lateral deformation of the diaphragm is less than or equal to 2 times the average story drift. The IBC does not explicitly define flexible diaphragm, but it does adopt ASCE 716, so the definition found there would apply for flexible diaphragms. So between these two definitions, the top one for rigid, the bottom one for flexible, all diaphragms fall within one of these two categories. So while ASCE 7 gives the 3 classifications, the IBC only requires that diaphragms be classified as either rigid or flexible. It means that the IBC never requires that a diaphragm be analyzed as semi-rigid. In ASCE 7, wind loads have a much simpler set of definitions. Most notably, whereas for seismic analysis, untopped still decks may qualify as flexible diaphragms, for wind analysis, they may qualify as rigid diaphragms. And so for wind analysis, most diaphragms will qualify as rigid. Let us now turn our attention to the Eurocode. I could not find any requirements associated with diaphragms in any of the Eurocodes except in Euronorm 1998-1, Eurocode 8 Design of Structures for Earthquake Resistance, and there are very few references to diaphragms there. Clause 4.2.3.2 gives requirements on diaphragm stiffness considerations in order for building to be considered regular. This in particular has reference to structures with multiple wings, such as an L-shaped building. If the wings deform independently, the structure is not regular. This section does not, however, give any guidance on the modeling of the diaphragm itself. The note in this section indicates that a diaphragm may be modeled as rigid if the diaphragm deflection using a semi-rigid analysis is not more than 10% greater than the deflection obtained from a rigid analysis. So you can have up to 10% difference. And when it qualifies as rigid, Clause 4 indicates that the masses and moments of inertia of each floor may be lumped at the center of gravity. This clause is related to the design of the diaphragm, not to analysis. The diaphragm must be able to transfer the forces into the lateral load-resisting system. This clause, specific to concrete buildings, indicates when a solid slab or topping slab may be considered to act as a diaphragm. This doesn't say rigid diaphragm, it merely says diaphragm. So the implication here is that if these conditions aren't met, the diaphragm should be analyzed as a flexible diaphragm. This clause, specific to precast concrete structures, requires that the diaphragm be analyzed as a semi-rigid diaphragm if it doesn't otherwise classify as rigid, as we discussed earlier. This requirement, specific to steel buildings, is merely a reference to the strength requirements discussed previously. And finally, this clause gives the conditions for which a timber diaphragm may be analyzed as rigid. The discussion on the Eurocode was brief. The references in the Eurocode are brief. And the intent was to point you to the applicable sections of the code so that you can study them more carefully. Again, any diaphragm can be analyzed as a semi-rigid diaphragm rather than turning to rules to determine if it needs to be rigid or flexible. Analytically, if you prefer to analyze the model as a semi-rigid diaphragm, that is certainly acceptable. So now that we've discussed some code requirements for classifying diaphragms, let's talk about how do you actually create the model of those diaphragms. So a flexible diaphragm is the same as no diaphragm. No diaphragm elements are modeled. There's no interaction between the frames and the diaphragm. The nodal loads must be applied directly to the frames. The rigid diaphragm is the same as infinitely rigid. And again, no diaphragm elements are explicitly modeled, but rather that diaphragm rigidity is represented as a stiffness, an infinite stiffness, in the stiffness matrix, and that's automated in the analysis process if you specify that your diaphragm is rigid. And the loads are applied, as shown here, as story forces. The forces are calculated or input, and then they are applied to points on the diaphragm, and then the diaphragm, that rigid analysis, distributes the forces out to the various frames. The semi-rigid diaphragm is represented by some matrix of stiffnesses. So the diaphragm elements are explicitly modeled. There's a mesh, and in the case of ram frame, that's automated. The diaphragm properties are defined, whether they're concrete or steel or timber or whatever they might be. And the loads are applied as loads on the mesh nodes. For semi-rigid diaphragm modeling, if you have a concrete slab, typically you would use the slab thickness, use the Poisson's ratio of 0.2 as for concrete. The elastic modulus E is as calculated for that concrete, and then you consider whether or not you need to apply crack factors. For a composite slab, concrete fill on metal deck, use the average concrete thickness, or conservatively use the concrete above the ribs. For Poisson's ratio, use 0.2 as for concrete. And for the elastic modulus, use the calculated value as for concrete. So essentially what we're doing here is we're ignoring the steel in the deck, and we're just going with the concrete. For a metal roof deck that's untopped, the thickness is merely the gauge of the deck. Poisson's ratio is 0.3 as for steel. And the elastic modulus, you need to use an effective elastic modulus E prime. This E prime is affected by the corrugations of the deck. They're affected by the attachment of the deck to the supporting beams, the span of the deck. So the calculation of this E prime can be rather rigorous. In terms of the loading on a semi-rigid diaphragm, the wind loads are applied to the nodes around the perimeter of the structure, and the seismic loads are applied to each of the nodes based on their relative contribution to the masses. And again, in ram frame, this process of applying the loads is automated. ASCE 716, section 12.8.4.2 has some requirements about considering that 5% eccentricity to account for accidental torsion. So if you look at the upper screen grab there, you see that the force arrows on the right have a higher magnitude than the force arrows on the left to account for the plus eccentricity requirement. And the screen grab on the bottom, you see that the force arrow magnitudes on the left are greater than those on the right to account for the minus eccentricity. Now for the good stuff. Let's talk about some case studies that will be useful in coming up with some recommendations and some good practices. For our first case study, let's take a look at this building. 4 stories. It's got concrete fill on metal deck, moment frames. There are 2 larger areas connected by a narrow corridor. This is the arrangement of the frames. Notice that they're asymmetric. There's 1 frame in the Y direction to the left and 2 in the Y directions on the right. So their coupling action will be captured in this analysis. And then 2 frames in the X direction. We'll be looking at the results for these individual frames, and so it's important to note the numbering. We've got frames 1 through 3 in the Y direction, and frames 4 and 5 in the X direction. And this is the shape of the floor with the location of the frames clearly indicated. So let's first of all talk about the influence of mesh size. The model is analyzed with 5 different mesh sizes: 1-foot mesh, 2-foot mesh, 4-foot mesh, 8-foot mesh, and 15-foot mesh. As a measure of the influence of the mesh size on the distribution of the applied lateral forces, the total shear at each level was determined for each frame. So first of all, this is what the 1-foot mesh looks like. And this is what the 15-foot mesh looks like. And here you can see a comparison between the 1-foot and the 15-foot mesh. So the question is, how much influence does mesh size have on the analysis results? After performing the analysis, we take a look at the frame story shears. And I tabulated those frame story shears for the 1-foot mesh. And we see here it was 126 kip at the top floor, 193 kip at the next floor down, and so forth. And so these values are tabulated there, indicating the story shear in frame number 1 for the 1-foot mesh. And I did that for each of the different mesh sizes, tabulated those story shears for frame 1 for each of the different mesh sizes. And just for comparison, I've put rigid on there, the results from the rigid analysis, because it's interesting to see that comparison. But our focus here mostly is, the question we have is, what's the appropriate mesh size to use? So the way to read this, if we look at the 5th floor, for example, we look at the frame story shears, and we look horizontally across the chart, and what we see is that for the 1-foot, 2-foot, 4-foot mesh, etc., there was virtually no change, and even the rigid diaphragm essentially had the same shear. So in this case, for frame number 1, there's very little impact on the mesh size. So then I did the same thing for each of the frames 1, 2, and 3, and so we see tabulated the values, and to make it much more useful, the magnitudes of the forces are not of so much interest, but rather how much the values vary. So if we assume that the 1-foot mesh is the most accurate, because generally it's perceived, and generally it's probably accepted that the smaller the mesh, the more accurate the result. If we compare the results of the 1-foot mesh to each of the other mesh results, what you see in blue there is how much the difference was. And as you can see, the difference is all less than 1%, less than 0.7%, whether the mesh is a 1-foot mesh or a 15-foot mesh. Now, once if we analyze the same thing as a rigid diaphragm, we're still really close, but we are starting to get some deviation. But keep in mind, this building wouldn't qualify as a rigid diaphragm anyway, and so we're seeing here why it shouldn't, although the differences are only at worst 11%. But something that's of key interest here is the analytical time. So first of all, at the beginning, when you create the model, the program has to take the time to create the mesh, the auto mesh. And what you see here are the times in that first line there. It shows the time for creating the mesh. And for a 1-foot mesh, for this model, it took 14 minutes and 45 seconds. And for the 15-foot mesh, it only took 1 second to create the mesh. Now, once the mesh is created, then it's done. And thereafter, every time you reanalyze your model, you have to go through the analysis times. And so you're repeatedly going to run into these times. And for the 1-foot mesh, it took 5 minutes and 41 seconds to analyze this structure, whereas for the 15-foot mesh, it only took 2 seconds. And so there's a significant difference here, and to be practical, we need to consider the time that we're spending in the analysis versus how much accuracy we're getting out of the analysis. And as you can see, from a time standpoint, there's little benefit in going to the 1-foot mesh in terms of the frame story shears. I also did the same thing for the frames in the X direction for frames number 4 and 5, but we see the same results. The impact of the mesh size on the analysis results are very, very small. So then I gave this presentation under other circumstances, and somebody said, well, you used moment frames in your analysis. Your brace frames are going to be worse because your frames are stiffer, and the impact is going to be worse. So I took the same model, but I converted those moment frames to brace frames and repeated the same process. So here now are my frames, and there's my floor, and I tabulated the same results, but now where the frames are much, much stiffer, they're brace frames. And now we look at the results, and now we're starting to see that the difference between the results for the 1-foot mesh and the 15-foot mesh in frame number 3 was 1.5%, and not particularly significant, but just something to be aware of. And now it's interesting here, the rigid diaphragm analysis become much, much less accurate. But like I say, this frame, this building never did qualify as for a rigid diaphragm, so this is showing you why. For this building, it would be inappropriate. But again, back to the mesh size, the difference between the 1-foot mesh and the 15-foot mesh, at worst, are 1.5% difference in the results. And again, I did the same thing in the X direction, and those results are even more favorable. So then, in addition to looking at the frames, I wanted to look at the forces in the diaphragm itself. What would be the impact of my mesh size in looking at the forces in the diaphragm? And so here, using ram frame again, I cut a section through the location where I want to obtain my diaphragm forces, and we can take a look at those. Looking at this model and looking at that location in the diaphragm, we extracted the forces based on the different meshes, and here's the results we get. So for earthquake load case 1, which is in the X direction, we get the values shown in the top set of tabulations, and for the earthquake in the Y direction, we see the values given in the lower tabulation. And now what we see when we go to look at diaphragm forces themselves, now we're starting to see a little bit more impact from the mesh size. So in particular, the 15-foot mesh, and keep in mind these bays are 30 feet, so 15 feet is half of a bay size. This 15-foot mesh is showing some significant differences. The 8-foot mesh is also showing some differences, but 5%, 5.1%, and the smaller meshes again are showing virtually no difference from that of the 1-foot mesh. And in particular, the moment is the value here that is of most interest in designing that diaphragm through that cross section. And the moment values are all, for any of the meshes, the moment values are all very similar. So then I wanted to take a look at drift. What's the impact of the diaphragm on my drifts? And so again, using ram frame, I identify the locations where I want my drifts to be calculated, and I obtain those values, and I do that same calculation for each of the different mesh sizes and obtain those values. So for the story drift, we look at these 3 locations, the 2 extreme points and the point in the middle, and we perform the analyses for each of the different mesh sizes and extract those values. And for the drift in the X direction, these are the values that we get for each of those 3 points, and the drift is listed for each of the stories. So for example, if we look at the drift at the center of the structure there at 135 feet and 75 feet, we look at the drift at the 5th floor. For the 1-foot mesh, the drift is 0.19 inches. For the 2-foot mesh, the drift is 0.19 inches. And for the 15-foot mesh, the drift is 0.18 inches. And the difference there is it's 4.9% less than the 1-foot mesh. So that's how you read this chart. Again, we see that some of the drifts, if you use the 15-foot mesh, exceed those of the 1-foot mesh by 5.5, 5.7%. So this is the impact that the mesh size has on the drift calculations in this structure. And I do the same thing for the drift in the y direction. And here now at the center point there, we see some differences of up to 6.2%. Keep in mind that by changing the stiffness of the diaphragm and by changing the mesh size, we are, to a degree, changing the stiffness of the diaphragm. That has an impact on the periods and the base shear that's calculated based on the code requirements. And so, again, I ran each of those models. I extracted the periods and the base shears. And if we look at the periods and the base shears, we see very minor differences based on the mesh size. But the mesh size has virtually no impact on the periods and the base shear. So based on all of that, and considering the analysis time, my recommendation is generally to go with the 8-foot mesh. And for those of you more comfortable with metric, that would be, say, 2.5 meter mesh as your maximum mesh size. And this is what that mesh looks like. We did see some differences in analytical results with the 8-foot mesh up to like 5%. And so if you're uncomfortable with that, if you feel that we even know earthquake forces to that extent, you could go down to a finer mesh, a 6-foot mesh or a 4-foot mesh. But generally, because of the quick analysis time, I'm really comfortable with that 8-foot mesh. And that's true for about every project that I look at. That seems to be the case. So we've talked about the mesh size. Let's talk now about the influence of the material properties of the diaphragm. And that can be significant. Take the case of a still deck, just a bare still deck. You've got these values of E effective that are based on a value of G effective that's shown in the equation down in the lower right-hand corner, and it's a function of several things, including the deck profile, the deck gauge, the fastener type, the pattern and spacing of the fasteners, the deck span, and these are going to vary across the diaphragm. You can have different conditions, which mean you have a different G prime, which means you have a different E effective. And technically, to be 100% correct, you would have to model each different area of diaphragm with different values. Is it reasonable to calculate a representative value and just use that across the entire diaphragm? Is the influence of these material properties that great on the distribution and on the diaphragm effects that it's important? Or take the case of a concrete slab. Should you consider cracking? If so, how much? Will that make a difference? Or is the influence of material properties similar to the influence of the mesh size? So for example, here's this floor. It's got different spans in different areas. The deck's oriented differently. Deck spans will be different. And so potentially each of these different areas would need to have a different diaphragm property. So is it necessary to go these extremes, or can we do something more simple? So my intent was, let's go back to that initial case study. Just take the roof off of it, or the top level, and assign a bare steel deck, and then create variations of the model with varying effective E values. And so I took that model and I analyzed it with 7 widely different values of effective modulus of elasticity. 500 KSI, 1,000 KSI, all the way up to 24,000 KSI. So a very huge range of effective E, and analyzed the model to see what the impact was. And just so you know, I used a 4-foot mesh in each of these runs. I kept the mesh size a constant so that we could just focus on the changes in effective E. So the question, how much influence does inaccuracy in the diaphragm properties, for example in E prime, have on the analysis results? So take a look at what this model is doing. You see that that diaphragm area on the left has significant rotation, um, and that's due to the fact that it only has one frame in each direction. There's nothing to prevent this area of the floor from rotating except for the thin section of the diaphragm which is grabbed onto it. And so the narrow diaphragm section is being relied on to provide stability and rotational resistance. And so as a result, that narrow diaphragm section is undergoing significant curvature. In a real structure, that behavior would engage the beam line. The beams would become chords. And in fact, in order to make that system even work, you would have to model in the chords. And so if we add those structural members to the lateral analysis, we do see significant improvement in the rotation and the deformation. Now the model that includes the chords, we're not seeing that same extreme rotation and deformation. And if we take a look at the forces in the members, we can see that they're quite significant. The members, the beams, take a significant portion of that entire force. It's not just all in diaphragm action. And in this case, for this beam, we see that it's carrying roughly 50 kip of axial force. So this was not a good model for examining diaphragm properties, since the diaphragm is not the dominant element here. The beams are actually the dominant element. So we need a model that's a little more conducive to looking at the diaphragm behavior, not a model such as this one that is really dependent upon the beams themselves. So I modified that example. I made it more realistic for what we're trying to look at. So if you'll notice, it has additional frames in both sections of the floor to prevent that rotation, and the narrow section isn't as narrow. And now the structure is not symmetric mass-wise and stiffness-wise. Neither model was, but in this one, again, it's still not symmetric. And so this model is still highly dependent on diaphragm behavior, and so it's a good test for what we want to see, but it's not so dependent upon like drags and chords in order to actually make it work. We can focus on the diaphragm in this model. So here are my frames, and here's the shape of the floor and the locations of the frames. And again, it was purposely created with an unsymmetric distribution of frames. We've only got one frame in the y direction on the left, but two in the y direction on the right. And there's an uneven distribution of mass. And the intent of that is to force the diaphragm to have to transfer the forces from one portion of the building to the other portion of the building. So we're relying on diaphragm action. And I would expect that the more common structures that have a better distribution of frames and a better distribution of masses, that they'll even behave more favorably than the results that we're going to see from this case study. But this is somewhat of an extreme so that we can really see the impact of the differences that the diaphragm section properties are going to make. So again, I went through the process, do the analyses for each of the different effective E's ranging from 500 KSI to 24,000 KSI. And in the X direction, we look at frames 4, 5, 6, and 7. And in the Y directions, we look at frames 1, 2, and 3. And what we find is that at the worst, for the frame story shear, frame number 6, for the 24,000 KSI value, varied from the 500 KSI value by 3.7%. Now, keep in mind, I'm not saying that 500 is the right answer. As an engineer, I haven't said this is the deck I'm going to use, and therefore the right answer for this model is such and such a value. I'm not making that decision right now. All I'm trying to point out is that if I make different decisions about effective E, these are the impact that's going to result. So even if my effective E is varying by a factor of 48 times between E of 500 and E of 24,000, my frame story shears only differ by 3.7%, which tells me that for frame story shears, the analysis is not sensitive to the effective E. So again, now let's take a look at diaphragm section forces. And when we do that, now we start to see more variation. The magnitude of forces in the diaphragms, they start to vary more based on the effective E that you use. So that would indicate don't be off by a factor of 48. Make sure that the effective E that you use is something close to what really is there in the structure. What we see here is that even if the effective E that's used is off by a factor of 48 times the proper value, the moment is only going to vary by 23%, 22.9%. So it indicates, if the proper value is 4,000, for example, and we specified an effective E of 2,000, we're only going to be off by the differences in those percents, just a few percent, rather than the large percents here that we're seeing for a very large variation in E. So then I wanted to do the same thing with looking at drift. And so first of all, I think it's instructive. Let's start out by looking at points that fall on the frames themselves. And so I looked at the drift at these 2 points, which are on the frames, and went through the same process using the analyses with different values of effective E, and this is what I see. So again, for drift in the X direction, the difference between using an effective E of 500 versus using an effective E of 24,000, the difference is only 4.7%. And so even the story drifts are only minimally impacted by a wide range of effective E's. But keep in mind, this is a point that's on a frame, and so really what this is showing you is the story drift of the frame more than of the diaphragm itself. So then I repeated the process, but now I used these extreme points and the point in the middle. On the diaphragm, which notice they are no longer on frames, they're just points on the diaphragm. And when I go through the same exercise, I find significant differences in the story drifts between the various values of E. Notice the value in the parentheses rather than a percent difference, which was shown in the previous slides. Now it's a fraction by which the drift differs from that of effective E of 500. So for example, if we look at the drift in the X direction at that first point, when effective E is 500, the drift is 5.9311. Compare that with the drift when effective E is 1,000, and that drift is 2.9802. And so the drift when effective E is 1,000 is 1 over 2 times the drift when E is 500. So the diaphragm that's twice as stiff deflects half as much. And compare 500 to 2,000. The diaphragm that's 4 times as stiff deflects 1 over 3.9 as much. So the deflections, the drifts now are roughly proportional to the effective E, as really we should expect. And this shows that when we're investigating drifted points on the diaphragm that are distant from the frames, these drift values are sensitive to and are roughly proportional to the value specified for E. Remember that this model has a very soft diaphragm. It has a still deck that's only 0.0199 inches thick, which is the gauge of the deck. What we see here doesn't pertain to concrete slabs or composite slabs because they are so much stiffer. They are way off to the right of this chart. The contribution of the deck deformation to the overall drift is so small that it's inconsequential for those decks. What we are seeing here is only an issue for decks such as bare metal decks. So faced with this, what should you do? First of all, how realistic are these numbers? The analytical model didn't include the gravity beams. They would have a significant restraining effect. So much so that I would suggest that the diaphragm in reality probably doesn't deflect at a point away from the frames much more than the deflection at a point on the frame that we were looking at moments ago. Those were smaller, more reasonable numbers. So from this case study, we learned that varying the diaphragm stiffness, even by a large amount, has very little impact on the distribution of forces to the frames, to the diaphragm forces, and to the drift at the frames. But it does have a significant impact on the results given for drift of the diaphragm at points away from the frames. And as we discussed, you need to be very suspicious of these drift results. So, based on all of that, let's talk about some conclusions to that and some recommendations. So first of all, it's important that you correctly categorize each diaphragm. Is it flexible? Is it semi-rigid or is it rigid? Of course, you need to correctly categorize that. Generally use the rigid diaphragm designation whenever you can because it's simple and it's faster. Take advantage of IBC's more liberal definition of rigid. Remember, the IBC indicates that every diaphragm is either flexible or it's rigid. It doesn't explicitly require that you consider semi-rigid, whereas ASCE 7 does. So take advantage of the rigid definition when you can. And remember the dichotomy here. Rigid is if the displacement of the diaphragm is less than 2 times the story drift, and it's flexible if the diaphragm displacement is greater than 2 times the story drift. And then for simplicity, use the same type of diaphragm in your wind analysis as for seismic analysis, even though the definitions of what's rigid and what's flexible may be different between those two. If you follow the seismic requirements, then you're going to be safe to use the same ones for wind. Remember that semi-rigid diaphragms can always be used for all diaphragms, even those that would otherwise, according to the code, qualify as flexible or rigid. It might be easier to model as semi-rigid than to go through the effort to figure out what category it's in. You just say, I'm just always going to model it as semi-rigid and just be done and go with that analysis. And so there's certainly advantages to that. It does require extra modeling care. You have to make sure that you take care of things like analytical instabilities and whatnot. So it is more work, but you can use semi-rigid anytime you want, and it may be easier to just do that. Use as large a mesh as is reasonable. The larger the mesh, the quicker the analysis. And when you're doing repeated analyses, over time, you're going to save time. And I like 8 feet, but again, you use your judgment there and what you're comfortable with. For solid slabs, such as concrete slabs and concrete on steel deck, the variations in material properties have negligible impact on the analysis results. So use reasonable values, but be practical on your precision there. For very flexible systems, such as steel roof deck, if portions of the deck undergo significant deformation while providing torsional restraint to a portion of the diaphragm, like what we saw, an analysis that doesn't include the chord members is probably inadequate. You probably, for a really sparse structure like this, you probably need to include those chords in that analysis. And for very flexible, again, for very flexible systems such as a steel roof deck, the influence of material properties for the story shear is negligible. Whether you use a very, very large E or a very, very small E, the effect on the story shear is going to be pretty small. So distribution of forces to the frames, to the diaphragms, has a small impact. Use reasonable values, but be practical. For investigation of drift, the variation in stiffness properties can have a significant impact, and you're going to have to figure out how best to deal with that and how best to trust the numbers that come out of such an analysis. And it's generally only a problem when you're looking at a point that's far away from a frame line. The closer you get to the frame node, the less impact this has. And then recognize that you may not have included the drags and chords and gravity framing in your analysis, but all of those have a probably significant impact in stiffening the chord and preventing the large deformations that you might otherwise see reported. In short, take the time to experiment and investigate yourself. You can create these same models or similar models or models that you're curious about. You can look at aspects that you want, but take that time to experiment and investigate so that you're comfortable in what's reasonable. You're not just taking it for me. You're looking at real structures, real models, and just take some time and get comfortable with that. And then in the end, don't be sloppy, but be practical. You know, how accurate do you really need to be to get the accuracy that you need for design? Based on all of the other things where we don't know how precise or accurate it might be, what's the value in spending an inordinate amount of time on your diaphragms when there are practical solutions that can be reached more quickly? So again, don't be sloppy, but be practical. So that includes my presentation today. I hope that was informative and useful. And if you have any questions or if you would like to correct me or make comments, feel free to contact me at alanadams@bentley.com. Thank you very much.